Okay, so today I will start discussing an interesting problem, which is the localized damping, right? So why I'm doing so? Well, yesterday we were considering the wave equation ytt minus Laplacian y plus yt equals 0 that we have rewritten in this manner, right? So that we can understand that the feedback is being applied everywhere. But this is definitely a limitation in the context of control problems, right? Because this means that if you know the membrane, right, or the acoustic waves propagating are occupying this domain, right, this will mean that the control, right, is acting everywhere inside. So this will mean that the whole domain, right, the whole domain will be full of actuators, right? We need indeed, you know, an actuator at every point X being able to apply a force which is precisely the velocity yt at that point X. So this will mean actuation everywhere in the domain omega, meaning that at each X we have an actuator able to realize, you know, the force F xt, which is equal to minus yt xt. Now, if you talk to, you know, practitioners of this kind of damping mechanisms, you will, you know, observe that they will tell you, well, listen, this is not very realistic. You never have, right? You never have actuation everywhere in the domain, right? So there are many applications of this kind of problems. There is one that we often experience and we don't even realize it. Sometimes they are not very visible, right? So we can see that on highways, right? So on highways, for instance, we observe that especially when new highways are built, right? Oftentimes, you know, on territories that are occupied by, you know, surrounded by residences, we often observe that there are barriers, acoustic barriers that are built, right? So these acoustic barriers can be sometimes solid walls, and some other times they are not even solid, they are just simply some piecewise constant material columns that are, you know, built so that the noise generated, right? So the noise generated by the cars when traveling, when getting to the border of the highway, is reflected inside, right? So that's the idea, you know? So this is a typical example where, you know, the damping, right? The damping is localized on the boundary of the domain, right? So this is a first observation. You see, in this case, someone could say, well, but what is the relation of the wave equation with this problem of noise propagation, noise generated by traffic on highways? Well, of course, the wave equation is the model also for acoustic waves, right? So the pressure field, the pressure potential of acoustic waves is modeled, at least in the linearized regime, by the scalar wave equation. And the problem of noise reduction, as we have mentioned in the early lectures of this series, is one of the main motivations, main applications of control theory, independent of what noise means, right? So noise can be acoustic noise, but it could be also the noise on a blurry image. Okay, so then you see that in this particular example, it is natural to think on damped waves, damping noise, absorbing noise, but when you do so, the damping term, the dissipative term, is only localized on the boundary, is not put everywhere inside. So here, actually, we need, right, this space completely free so that cars can travel. We cannot claim that we are, say, embedding some kind of damping mechanism within this medium along the highway. The highway needs to be free so that cars can travel with maximal visibility and without any obstacles, so to make traffic safe, okay? So the damping is on the boundary. This means that, you know, in particular, it will be very natural to consider situations where, you know, this elastic body or this cavity in which acoustic waves are propagating, so that both examples will be relevant. So elastic body or medium in which acoustic waves propagate, it's very natural to consider the situation in which the damping is only localized here on the boundary of the domain, right? So here we will be considering the case where the damping localized on the boundary, right? If you think more on mechanical terms, this simply corresponds to the fact that what something that we do often in practice, in which we take some kind of elastic body and then I apply forces on the boundary in order to, you know, reshape it, modify its shape, right? So I'm not acting inside, I'm really acting on the boundary, because the boundary is really the part of the domain to which we can really have access, right? So through applied boundary forces. Okay. Another motivation in which is, so in this case, the localization of the damping will be on the boundary. Okay, so this is an example in which we say we are looking to localize damping, right? And then the localized damping can be either on the boundary, like in these examples, or in the interior, right? What will be the example of an interior control problem? Well, it's an example in which you simply say, well, I go back to, you know, to the domain before, right? In which, you know, either elastic waves or acoustic waves are propagating. And then I know that I can use some patches, right? So these are the actuators, damping or controlling waves. This is something also we can do. We can always place, you know, there are sometimes you see that in modern buildings somewhere as well, right? So there are big rooms in which you have a small column, right, which is kind of a decoration, but this column is made of soft material that is able to absorb waves, right? So this allows to improve the acoustic propagation on big rooms, right? So that all the possible reflected waves on the boundary are absorbed by these absorbing columns, right? That in this way reduce the echoes, right? Making the acoustic signal much more clear, neat, and transparent, okay? So this is also a possibility that you could think of, right? So having absorbers, actuators that are located somewhere inside the domain. What is the simplest model for this? Well, it will be to, you know, given the domain omega, of RD, right? We are in dimension D greater or equal than 1. In 1 is the one-dimensional D'Alembert equation for the propagation of waves, right? And a subdomain, a small omega included in the large domain capital omega, right? We consider the wave equation with damping localized in a small omega, right? So the model will then read ytt minus Laplacian y plus the characteristic function of the set small omega equals 0, y on the boundary is equal to 0, some inertial conditions, right? Okay, where 1 over small omega is the characteristic function of a small omega, meaning that the value is 1 in omega and 0 outside. So what does it mean? It means that the wave equation, if we write it down in the classical, say, mechanical interpretation of, writing down the damping term of the right-hand side so that we see indeed the impact of an applied force, the wave equation is 0 in omega minus small omega. This means that waves travel freely when, they are away from the actuation zone small omega, and then is a velocity damping in a small omega, right? So generally speaking, if we will, be in the situation where this is the cavity small omega, and this is the region in which, the absorbing column is placed, right? So, waves will travel freely, right? If there is some kind of, emitter, right? Emission, post of acoustic signals, they will propagate freely, right? And they will be absorbed, right? Or damped only when the signal reaches a small omega, right? Small omega. And then the question we analyze is the following. So the question is then, can a localized damping mechanism be efficient, right? And being efficient means at least two different things. The first one is whether the energy of the solutions goes to 0 as t goes to infinity, right? That's the first thing, right? In case the energy of the solutions will not go to 0, this will mean that we have missed some of the vibrations of the system, some of the Fourier components, part of the energy of the system was not dissipated. So we could say, well, this is not such a efficient mechanism. But if we are not satisfied with this convergence, we could also, look for a more demanding property of exponential decay, right? So that, of course, is much stronger than simply having, the energy going down to 0, right? Because going down to 0, it could be that the energy goes down to 0 polynomially, it could be logarithmic, it could be log, an iterated logarithm, something that is extremely slow and that in practice is not so efficient, right? In case we have a given time window, because in practice, right, you need waves to be dissipated, right, before too much time, evolve, right? So in particular here, in this problem I was discussing here of the, the damping, the effective damping of say, the acoustic signals generated by the engines of the car, right? We essentially need the dampers to be efficient just by the first contact of waves with, right, the damping material, right? Why? Because, you know, if the damping was not efficient just in one shot, this wave will bounce back, generating some kind of resonance, right? So typically, we are more interested on this kind of very effective exponential decay rate rather than this simply generic convergence result, right? Because although mathematically is very interesting, in practice, it doesn't say that much, right? Okay. So then actually, right, I said something that is not completely rigorous, right? I said, well, if you have, you know, if you don't have exponential decay, you could have slower decay rates like polynomial or even logarithmic. Is this completely true, right? So there is a comment here to be made. It's a comment on analysis of dissipative semigroups. So the remark is the following. If a dissipative semigroup decays, then the decay needs to be exponential. So that's surprising, right? So this seems to indicate there cannot be semigroups that decay slowly. Let us analyze better what I mean by this, right? So this is a very classical result on the classification of dissipative semigroups. I don't really remember who did that for the first time, right? But certainly, you know, the pioneers of the extension of, you know, the dissipative wave equations from finite to infinite dimensions were very much involved on this, right? Let me consider a semigroup, right, which is dissipative. So what does it mean, the semigroup to be dissipative? It means that, you know, the norm of the semigroup for every t as a linear map from, say, the Banach or the Hilbert space capital X, where it is defined into itself, right? So in the case of the wave equation, right, for the wave equation, this space X is simply the energy space. The solution belongs to H10 and the velocity belongs to L2. And I need to do it so because, you know, as it is typical for the theory of dynamical systems, we don't like looking to dynamical systems which are second order in time. We rather prefer to say, well, I can always write this as a first order system in which yt is equal to z, the auxiliary variable given by the velocity, and then I can rewrite the second equation as being simply minus Laplacian y minus z, right? And then if you look to the natural space in which this problem has to be written, then you realize, because of the conservation of energy or the dissipation of energy, that the energy space is the natural one, so that the component y belongs to H10 and the velocity z, which is actually the velocity yt, belongs to L2. Okay, good. But this applies, I mean, the result I am discussing here is completely general. I give you a semigroup which is dissipative. So this simply means that, you know, whenever you take a trajectory, right? So if you take now, given x0 in x, you look to the corresponding solution generated by the semigroup STx0, right? You can definitely guarantee that the norm of STx0, right, in x is less than the norm of ST1x0 in x if T2 is greater than T1, right? Why is that? Why the norm of, you know, the semigroup at any time being less than 1 allows me to guarantee this decay property? I have to be a little bit careful, right? Because if I will compare simply here the norm of ST2 x0 with x0 and ST1 x0 with x0, I will not get a comparison between T1 and T2. What do you suggest in order to really understand the comparison of the trajectories in two different time instances? Is any hint about this? In fact, you need to use the fundamental property of semigroups, right? Because we know that if T2 is really T1 plus some positive time, right? Then I can always say that S2T applied to x0 is ST1 plus tau applied to x0, right? And this is S tau applied to ST1 x0. This is the fundamental semigroup property associated to autonomous time-independent dynamical systems. And therefore, right, the norm of ST2 x0, right, in X is going to be equal to the norm of S tau, ST1 of x0 in X, and this is less than the norm of S tau as a linear operator from X to X times ST1 at x0. And this is, therefore, right, something that is dissipative, right, because of the hypothesis that the norm of ST is less than 1 for every one, right, for every T, in particular for tau, right? So you see that this immediately generates a trajectory that is going down. And then the dichotomy says that, you know, if there is some decay, then the decay needs to be exponential. Why is that? Assume there is some decay. Okay, so let me do this argument. Assume that the semigroup decays. So this means that the norm of the semigroup as a linear operator from X to X is equal to some function phi t that goes to 0 as t goes to infinity, right? Okay, this makes sense. Now, you agree with me that if phi t goes to 0 as t goes to infinity, then there exists some time capital T for which the norm of phi t, right? Sorry, this will be just the absolute value because we are simply here considering norms. So these are positive numbers, is equal to gamma, which is less than 1. Actually, I could make it as small as I wish, right? But take any, just to show you that in this argument, this is very soft. You just take capital T long enough, right? So that the norm of the semigroup is guaranteed to be smaller than 1, right? Okay. Then, if I look to the semigroup property, what happens then when I look to the norm, right, of S k times t, with k an integer number? Well, you see that if you apply, right, yeah, the semigroup property in an inductive manner, right, you will find that this is less than gamma to the power k, right? So if the semigroup in a time horizon of the length capital T shrinks norms with a factor gamma, when you iterate, this is like, again, like in Banach iteration for contractive maps, right? In a time interval k times longer, k times capital T, then the compression factor will be gamma to the power k, right? But then what happens? Give me any t large, right? Then this t, you will be able to write it down as k times t, right? Capital T plus some factor, right? Tau, which is in between 0 and capital T, right? So this is just the decomposition, right, of t as multiple integer multiples of capital T plus some fractional residual, right? Irrational residual. Okay, so then the norm of ft, which is the norm of skt plus tau, right, will be less than the norm of skt, right? Why? Because the semigroup is dissipative, so this extra, right, this extra tau time that I let, which might be very small, so I cannot quantify the effect of this remaining tau time interval, definitely this produces the decay farther of the norm, right? So this means that, you know, the norm of ST for sure will be less than the norm of SK capital T. But we have seen that this is less than gamma to the power k. And gamma to the power k, I can always write it down as exponential, right? Log gamma k. Of course, gamma being less than 1, the logarithm is negative, so I can write it better that way, right? So to illustrate the decay rate, right? But the decay rate, then k, I can write it down. I can always guarantee that k will be larger, right? So k will always be larger than t minus capital T divided by tau, right? So then I will get here the log of gamma in absolute value, t, t minus capital T divided by t, right? And therefore, I will have a decay rate, which is a number here, which is exponential of minus the logarithm. So here I will get, log of gamma times t, essentially, right, with a constant c. So we see that in that case, because of the fact that just for some time, right, for a some time value, gamma is less than 1, right, we get here a decay, right, which is of the order, the exponential order, the exponential decay, right? Sorry, there is a capital T here, right? The exponential decay rate is of the order of the log of gamma divided by t, right? And it makes sense, right? So it makes sense that the decay rate depends both on gamma and capital T, right? Because somehow when you write this down, both capital T and gamma give you a measure of the dissipativity of the system, right? Of course, you could normalize things to say, well, because phi goes to 0, rather than looking at generic gamma, I will take gamma equal to 1/2. I can always check just the dissipativity rate out of the, you know, of the time instance in which the semigroup reaches the level where the norm is 1/2. But then, of course, how effective the dissipative system is, once you set up, you normalize here the norm of the semigroup to be 1/2, how dissipative the system is will depend very much on how much time, capital T, you waited until the semigroup has reached the level of contraction 1/2. And this is why it is natural that, you know, the decay property is finally normalized as a combination of gamma and capital T, right? So you see that actually what I have shown is that if there is some decay, the decay is exponential, right? So, but what does it mean? It means that when I'm talking about the decay, in particular in the context of the wave equation, so for the wave equation, right, I will be writing inequalities like this, right? So wave equation with dissipation, I will be writing inequalities like this. And then what I'm saying is that if phi t goes to 0, right, as t goes to infinity, then necessarily this produces an exponential decay. And then you wonder why. So there cannot exist then semigroups that are slowly decaying as t goes to infinity. There has to be, right? So what about, you know, what about semigroups with a slow decay, right? So I could certainly take, for instance, just, you know, you can always build abstract dynamical systems in little L2. This is the prototypical space of infinite dimensions in which you can build a specific semigroup just choosing the corresponding matrices. And you can certainly build semigroups, for instance, in which, you know, the spectrum, right, of the corresponding semigroup is something like this. So is, you know, all the spectrum, you know, all the eigenvalues lambda k as such as the real part of lambda k is always negative. So you will have the dissipativity of the system, but so that the real part of lambda k goes to 0 as k goes to infinity. Of course, in order to build such a, you know, infinite dimensional system with infinitely many, say, eigenfunctions and eigenvalues, right, you need the infinite dimensional context, right? So you could do that, for instance, you know, so this is the spectral representation of a dissipative semigroup in, for instance, the Hilbert space, the infinite dimensional Hilbert space L2. And then in that case, I claim, well, listen, there is something I don't understand in this statement, because in this example, it looks like, of course, the energy will go down to 0 as t goes to infinity for every solution, right? Because all the eigenvalues are negative, so all the components are going down, all the components are eventually dissipated, but definitely, right, this is impossible. The decay rate, the exponential decay rate is impossible, right? Why? Because whatever the alpha you give me, if alpha is over here, right? If you draw the alpha here or minus alpha here, you will see, well, this cannot be true, right? Why? Because there are eigenvalues whose real part is going down to 0. So regardless how small the minus alpha is, right, there is always an eigenvalue which is to the right of minus alpha and is contradicting this decay rate. Then the question is, where is the contradiction? So on one hand, I'm saying that, you know, if a semigroup decays, then there is exponential decay, right? Okay, there is exponential decay. On the other, I'm saying that there seem to be examples where all the trajectories go to 0, but for which there is no exponential decay. Do you know why these two things are compatible? The reason for this, so both results are compatible since, right, the fact that ET goes to 0 for all solutions is much weaker than the norm of the semigroup as a linear operator from X to S to be a phi t that goes to 0, right? In other words, when ET goes to 0 as t goes to infinity, the decay rate may depend on the solution, right, and be compatible with the fact that the norm of the semigroup, right, is equal to 1 for all t, right? So this is a typical example. If you will consider the norm of the semigroup here, that's a bit surprising, right? Because this is the semigroup generated by such a spectrum, right? So I'm talking here about simply, you know, the example I am considering is simply, you know, in the space L2, I consider the eigenvalues lambda as above, right? Then given any initial condition x0, I am writing down this x0 as, you know, a linear combination of the eigenvectors on the canonical basis that I was discussing yesterday, where in little L2, the canonical basis is simply the kth eigenvector is simply, or the kth element of the canonical basis is 0, 0, 0, 1 in the kth component, and then 0, 0, 0 again forever, right? And then the semigroup I am considering here is simply the one that is damping, right, each component of this Fourier decomposition, or this decomposition on the canonical basis with the corresponding eigenvalue lambda k, right? I draw again the, you know, the eigenvalues, right? And then if you look to this map, right, if you look to the map that to x0 associates the norm of xt, right, in, say, the space of linear bounded operators from L2 into L2, right, you see that the norm of this operator is equal to 1. Why the norm of this operator is equal to 1? Of course, the norm of this operator is less or equal than 1. Why? Because if I take the norm of xt in little L2, because of this Fourier series representation, the norm squared will be simply equal to the sum for k greater than 1 of x0 k squared and then exponential 2 lambda kt, and this is less than the sum of k on k of all the Fourier components, which is just the norm of the initial datum in L2 squared. And this is so simply, why? Because all the real parts of all the lambda k's are negative. So this immediately means that the norm of the semigroup, right, as an operator from little L2 into little L2 is less or equal than 1. But I ask you, is it less than 1 really? And then I tell you no, because whenever you will choose a number, right, whenever you will choose a number, gamma, which is less than 1, you could always find, right, a lambda for k very large, which is even slower, right? So on the other hand, right, the fact that st as a linear operator from L2 into L2 is a number less than 1 is impossible, right? And this implies that the norm of st eventually from little L2 into little L2 is equal to 1. So this is an important warning, right? The warning is for infinite dimensional systems, the decay of each trajectory, right, is compatible with the absence of decay of the semigroup. Okay? And then the two examples that, you know, tell me this are the following, right? So I give you example 1, right? So this is example 1, and this is example 2, right? In example 2, I assume that there is some, a spectral abscissa, and that the semigroup, all the eigenvalues are to the left of this green line with abscissa minus alpha, which is negative, right? And in the first example, I consider the semigroup where, in this first case, the real part of lambda k goes to 0 as k goes to infinity, while in the second case, the real part of lambda k is always less than alpha, less than 0 for all k. What do you think is going to be the behavior of each of these systems? In which of the systems, example 1 or example 2, will the energy of the solutions behave according to the exponential decay property, right? So if this is our goal, right? If this is our goal, the exponential decay property, which of these examples will fulfill it? Example 1 or example 2? What do you think is the answer? What is decaying better, example 1 or example 2? It's of course example 2, right? Example 2 typically corresponds to an exponential decay rate. While example 1 corresponds to an arbitrarily slow decay rate, right? Why arbitrarily slow? Well, because whenever you choose, as I said above, whenever you choose a minus alpha here as, aim of your decay property, you will always find eigenvalues that are decaying even slower, right? Okay, so this is very important. This is a new phenomenon. Of course, this cannot occur for finite dimensional systems, right? Because for finite dimensional systems, you have finitely many eigenvalues. It doesn't really depend how many you have. N can be very large. But if n is finite, right? If n is finite, then as soon as all eigenvalues are to the left, then they are to the left of some spectral abscissa and you have exponential decay, right? Yeah. And then as Yao Wan is saying, right, this indeed is a situation where we can talk about simply stability, right? While in here, we will talk about exponential stability. Good. So then you see that from a mathematical perspective, both questions are interesting and are worth being analyzed. Now, from a practical perspective, however, you understand that the second option is much more attractive, right? Why? Because if you will, prove simply, right, a stability property without such an exponential decay property, this stability property as such, could be compatible with a, say, damping mechanism, a dissipative system that is very, very, very weakly dissipative at high frequencies. And then if you were, in this context in which, you were in this context in which you were interested on, dissipating, where is the drawing? You were interested on dissipating waves on the highway, right? You could say, well, you have built, a damping mechanism that is efficient for low frequency waves, but maybe is not efficient enough for high frequency waves. So this will mean that, for instance, you are able to, assure that the noise generated by cars traveling at low velocity is properly, absorbed by these acoustic absorption mechanisms, but, the acoustic waves generating by cars at higher speed is not absorbed, and it passes through, the walls to get to the, to the areas where people are working or are living, right? So this, from a practical perspective, is much weaker than that, right? So of course, exponential stability is much more useful from a practical perspective since it guarantees that all frequencies are effectively damped, right? Exponentially uniformly. So our last comment is that, okay, so now if you receive a paper, you are a referee, you have to evaluate a paper, and then someone says that for a damped wave equation, right, the paper claims I have a decay rate of the order of 1 divided by 1 plus t, right, for all t and for all solution. What could you immediately remark out of this apparently slow decay rate, right? So you receive a paper and the author says, oh, I have an example where the decay rate seems to be polynomial. I mean, it's polynomial in the denominator. I mean, it's a fractional function, of course, right? But it's polynomial in the sense that the decay is like, a t, right, to the power -1. If you receive a paper saying that, what can you say? You say, yes, I mean, that is possible. But if someone has proved this, then you can immediately guarantee that there exists T and alpha positive so that, right, you have something like this. Okay? So when some people, when people say, I was able to prove for a damped linear wave equation, right, that, there is a polynomial decay rate like this, you say, well, this is fine, but in fact, you didn't exploit the full power of your decay property, because out of this, you can prove this. What is the proof? The proof is the same as above. You take a gamma smaller than 1, for instance, gamma equal 1/2. For t large enough, you know that the semigroup map from E0 into ET is going to be of norm 1/2. Then you iterate like in Banach contraction, and you get the exponential decay rate. So it's not that saying this is wrong. It's that when you say this, somehow you are underestimating really the decay properties of the system, right? So this is the first remark. But very often what you find is decay properties like this, right? Sometimes people say, well, I was able to show that my semigroup, right, decays like 1 + 1/t, but now in this estimate, I have used, right, the norm on the domain of the operator. And then in this case, of course, the norm on the domain of the operator is much stronger than the natural canonical norm in the space X. So you are not really talking about, mapping X into X. And actually, if you try to apply here the iterative algorithm, the iterative argument before, like in Banach construction, to show that out of a slow decay, you can achieve the exponential decay, you will realize that it doesn't work, right? Why? Because you can apply this argument once, you start from an initial datum in the domain of the operator, and then you wait long enough so to decay like 1/2, but then the decay property you get is with values in X. And then you cannot use this argument again, you cannot iterate here again, because now you are not in the domain of the operator, you are not in the domain of the operator anymore, but you are in X. So the fact that there is a gap in these two spaces forbids you to iterate the decay, so to achieve exponential decay out of decay. And actually, this is what you see in this example, right? So if you give me the example of the semigroup in which, the eigenvalues are doing something like this, where the real part of the eigenvalues is always negative, but the limit as k goes to infinity of the real part of the eigenvalues, right, is equal to 0. And then you consider the corresponding semigroup, the one we wrote before, right? Okay. So here, as we have seen, right, the norm of this semigroup as a semigroup from L2 into L2 is equal to 1. This means that here there is no uniform exponential decay, but despite of this, we can achieve some decay if we impose further conditions on X0. For instance, as to give you an example, let us consider the case where the real part of lambda k is equal to -1/k, okay? So this is the typical example in which the real part of the high frequency eigenvalues, I mean, the damping operator is effective, is very nice. The damping operator is being able to damp every frequency of the system, but when frequencies are very high, the damping is a little bit slow, right? It's like we ourselves, okay, we can work very hard, we can be very fast, and then we can, study one topic and then the other and then the other, and then, but then of course we have a limit, right? And if the, if the pattern, if the flow of work is too high, we will not be able to track it efficiently anymore, right? So the same for the damping mechanism. You can have a damping mechanism that is very good, right? Has been designed very carefully, but of course it has some limitations. There is some rigidity on this damping mechanism, and this damping mechanism is not able to damp efficiently the very, very, very high frequencies. This will be the situation. So let me consider the situation example in which the real part of the eigenvalues is -1/k. But I tell you, well, but you see, being X0 being in L2 will simply be that the sum of all the squares of the components is finite. I will give you some further information. I will give you the information that the initial datum is on what could be, the discrete analog of the Sobolev space H1, in which you have further information on the integrability of the sum, like in Plancherel's identity, right? You have this. Okay. So my claim is that in this case, we can achieve polynomial decay. Why is that? Well, because take your solution, right, which is just the sum of x0k exponential lambda k t E0k, right? Take the norm in L2 square. And then, you know, because the real part of these eigenvalues is -1/k, and the imaginary part, of course, doesn't count in terms of the modulus is really the same. This is an orthonormal basis. The norms of all these eigenvectors is 1, right? And I get this. Okay. But now we have observed that, you know, with a power k square, right? With a power k square, this, you know, this sum is still integrable. So I can here multiply by k square, and I can divide by k square, right? Then this, you know, this will be less than the sum of k square x0 square, right? Which is the norm of x0 in a space which is definitely stronger than little l2. I call it little h1 because it corresponds to the discrete version of the Sobolev space h1. So this means, you know, when you are imposing this kind of the finiteness of this sum, this means that the energy of the system at high frequencies is necessarily small, right? And then I will have here, right, multiplying this by the supremum on k of exponential minus 2t/k divided by k squared. And now I ask you, is this supremum bounded? Can you find an upper bound for this? And the answer is yes, indeed. This quantity, right, is uniformly bounded, right? Why? Because I can always get the following bound. I can always write that 2t divided by k divided by k squared. I can see it as, say, you know, the denominator k/t, right? I could write it down like here, right? Then this means that I have to multiply by t squared. And then this is exponential minus 2t/k, right? And therefore, with the change of variables, say t/k equal to s, right? I have here the function exponential 1/t squared, and then here exponential of minus 2s divided by s squared, right? Of course, because the exponential decays much faster than the polynomial, this quantity is bounded, and therefore you see that you have a decay of the order of t squared, right? So this is a typical example where I can prove, right, that the norm of the solution xt in L2 is less than a constant times divided by t, not t squared, but t, because in all these computations, just to make them simpler, right? So I'm taking here a square of norms everywhere. So eventually I get this c/t, but to the price, and this is very important, right? That here, right, I am taking the norm of the initial datum in a stronger space, right? And then, right, this does not provide information on the norm of the semigroup as a linear operator from L2 into L2. This is just giving much less information, right? Because I am restricting the semigroup to a compact set, which is the one associated, say, to the unit sphere in this stronger norm. Okay, so this is important to take into account. This being said, once you are dealing with infinite dimensional dynamical systems, of course, it's very interesting also to analyze whether the energy goes to zero or not. This is the first thing you have to do, right? Okay, but you have to be careful, right? There could be situations in infinite dimensional cases where even if the energy goes to zero, this doesn't mean that the damping coefficient or the damping term is acting so efficiently, you could be really in a situation where the high frequency components decay very slowly. And of course, in practical applications, this is what we rather prefer, right? We will always prefer the exponential decay, right? But sometimes also, you know, very often in practical applications, people are not considering all the possible frequencies on the system. So very often when you are dealing with some, you know, practical application, right, we are considering a given frequency band. This means that we are mainly interested on damping a number of eigenvectors. And if you are really efficient and damping, you know, these frequencies, then things are fine, right? So for instance, we also know as humans, we are animals, and we can, you know, here we can perceive a given frequency band. And then if we are simply interested on noise reduction, right, for humans, then there are, you know, damping mechanisms that are efficient enough, but we realize how, you know, there are high frequency noise that maybe is fine for humans, but that, for instance, could bother the panda bear or a whale on the sea or a dog, a pet at home, right? So why? Because not all animals are hearing the same, are perceiving the same frequency band, right? So depending on the application you have in mind, if you have in mind simply reducing noise for humans, right? Something like this could be efficient. What I'm telling you is that if the mechanism you have chosen, right, is like this, as soon as you are not only interested on humans, but you are interested on other, say, animals, right, that will be able to listen to this, say, much higher frequency band, then you will realize the decay rate is maybe too weak. And this is what explains that while humans are calm, they don't hear anything, all elephants are escaping because they are able to perceive these higher frequency non-damped modes. Okay, very good. So then, anyhow, going back to this wave equation, let me explain you, right, what was done in the 70s by, I mentioned yesterday the names, right? People like, you know, Constantin Dafermos and Alain Aron, among others, of course. You know, the list is always longer. In the 70s, right? They said, okay, I have that the energy of this system is the same as for the wave equation. And this energy, the dissipation law for this energy is that, you know, the dissipation law is that the derivative of the energy is equal to minus the integral over omega squared of yt squared dx, right? Okay, so this is the domain omega, and this is the cavity, right, on which, you know, the damping is effective, right? And they said, what can I do with this? What was the argument yesterday? The argument yesterday was that, you know, what we have seen yesterday is that when a small omega is the whole domain capital omega, right? An argument in which we modify using the hypoellipticity ideas, right? We augment the energy from E into E epsilon, right? And this allows to observe the dissipative effect on the potential energy. And this led to exponential decay. But here things are more tricky, because you see, I'm only given the kinetic energy in the dissipation law. I only see the kinetic energy in a small omega. In order to apply the argument in here that we developed yesterday, to be able to achieve estimates also on the potential energy, first of all, I will need to be able to propagate the information I have in a small omega, right, into, you know, the whole domain omega. So the question is there a way, right, that I can propagate this information, right? So can we, you know, can we out of the dissipation of the energy on a small omega guarantee the effective dissipation of the kinetic energy everywhere in capital omega. Can we do that? Well, this is something that is tricky, right? So you see that when you are dealing with partial differential equations, you find somehow the need of, you know, playing with A and B, like in the Kalman-Rank condition, in two different ways. So what we did yesterday was to say, well, listen, the wave equation, right? What we did yesterday was to say, listen, the wave equation can be written as a first order system. And I am able to show that I don't need to dump the two components of the system. It is sufficient to just dump one, the kinetic one, for instance, because if I dump the kinetic energy, like in here, right, I can transfer this dumping on Z into dumping on Y, that by this argument in which I'm using, you know, a perturbation of the energy. This is exactly what you can do for the harmonic oscillator. It's the same, right? So there is a system pattern on the wave equation. And what we did yesterday was to disclose the interaction between the A and the B, like when we consider general dissipative, say, equations where the generator A was anti-adjoint. And then we were able to see that dissipating also through B was able to dissipate the full energy of the system. So here, yesterday, what we did, we used Kalman, right, in order to cope with the algebraic coupling of the system, right? But under the condition that the damping was effective everywhere. Today, we are in a much more complex situation, because the situation today is that the damping is only effective in a small omega. And I will need to know whether also the damping, so, is effective, for instance, at this point. At this point is away from a small omega. Well, you could think, well, anyhow, this is a continuum mechanics model. And of course, there is some link between this point and this point, right? Because there is a Laplacian there, and we know that the solutions cannot be computed like a parametric ODE, in which for every x I have a different component, but they are interlinked through the partial differential operator in x also. Yeah, that is true. But if you adopt this point of view, definitely how many x's I have? I mean, there is a continuum of x's outside the small omega. So this by no means is something that the Kalman-Rank condition can understand, right? Because the Kalman-Rank condition is fine for algebraic structures. When you have finally many components, then you can just, like in the Rubik cube, right? You can iterate B, AB, A squared B, and so on. And then you can fill the whole system and get complete information. But here, this is a continuum system. Even though you cannot exclude that this damping which is acting locally, has a global effect, this is an infinite dimensional problem. This is a continuum problem. It's not something, you can get out of Kalman, right? So the question is, does local action produce a global effect? But it is of infinite dimensional nature and cannot be handled through rank conditions. In order to understand a little bit better, let me consider first the case in 1D. Is the D'Alembert equation, right? So in 1D, we are just considering, right? So this is X. So I take, for instance, the interval from 0 to L, right? Okay. So this is the case where, 0L is a elastic. This is a elastic string of length L, right? So this, the vertical variable denotes time. This is the horizontal one denotes space. So waves are propagating here. And we know that because of the explicit representation formula of the solutions of the D'Alembert equation, D'Alembert said that solutions of the wave equation are just transport to the left plus transport to the right, right? What initial, say, disturbances on, any point of the string under vibration, you put this string vibrating through some initial action that is acting locally, so you pull the string, right? Then, this produces a signal that propagates to the right, right? This signal can also generate a wave traveling to the left, right? But each of these signals, right, bounces back again, right? Okay, so this is the typical picture, right? So the wave equation is just the superposition of many of these motions, right? This front here corresponds to Fx plus t because waves are traveling to the left with velocity 1, right? And, this one travels to the right with velocity, right, 1 as well. And then this generates a dynamics, which actually is periodic, right? So this generates a periodic dynamics. Why? Because you see, if you will continue this purple ray a little bit longer, right, you will realize that at a given time, you are at the same location. And if you will follow this red ray a little bit longer, you will realize that at the same time, the other broken line, gets to the original location. Could you please tell me what is the time needed for waves to come back to the original location here? What is the time needed to see that waves are coming back to the original configuration oriented in the same direction? 2 pi. The length is L here. The length here is L. The length being L, what is the time that this wave needs to follow this path and get here? It's going to be 2L, right? Because you see, what is this, if the velocity of propagation is 1, what is the time needed to cross the full domain? I mean, from right to left is L, because L is the distance that I am traveling on the x direction. And when you look to this broken segment plus this broken segment, you see that the travel distance is again this plus this is equal to L. So eventually you get, you know, this generates a period dynamics of period 2L. It's true that often we write this system in the interval 0 pi, because in this way we get rid of many pi's appearing in the Fourier series expansion, right? And then in that case, the periodic behavior in time is of period 2 pi, right? But in general, if you give me a string of length L and the velocity of propagation being 1, then, you know, you have a period of periodic behavior of period 2L. Of course, you can also modify coefficients here, and then by scaling, you can always compute this periodicity, right? So this is a very interesting example. So by the way, why is it true that, you know, when you solve the wave equation, the solutions are fx plus t, waves traveling to the right, plus waves traveling to the left and to the right? Well, the reason is very simple, is that, you know, for partial differential operators, you can use classical operations, right? Extend it to PD operators, right? And then you see that, you know, the wave operator, right? So the D'Alembert operator is decomposed into a transport operator and another transport operator. This transport operator is pointing to the left, and this transport operator is pointing to the right. They are both simplest examples of the transport equations we were considering yesterday. Okay, very good. So why I'm discussing all this? I'm discussing all this because the problem we are now interested in is, okay, so this will be the free D'Alembert equation, no damping, okay, no damping on it. We know that this is an ideal model. There is no any friction, right? The string will be vibrating forever. The acoustic wave will be propagating forever with the same amplitude. There is no friction, right, at all. This is not something that we experience in practice, right? All mechanisms experience some fatigue. So if I was now damping over here, if this was the damping region, right, what do you see? What do you see if now I draw, you know, the typical example in which this medium that was purely elastic and on which waves were propagating without any friction forever in a completely periodic pattern. Now I say, well, but I was able to place, right, in part of this string, I have taken the string, and in a part of it, I have put a damper, right? So the material here is softer, or I have glued some kind of actuator, right? So that, you know, when waves pass through, they are dissipated. Then you say, well, so this is true, even though this is not a Kalman problem, and it's not something I can analyze using rank conditions, because it is in nature an infinite dimensional problem. It is true that all waves are passing through the damping region, right? It doesn't really matter where you start, right? So you could start here, and point to the right. In principle, you are escaping the damping region. Assume you try to build, you don't believe me that this damping in a small omega will be sufficient for the exponential decay. And you say, well, you see, Enrique, I will build a wave that will escape the damping region and therefore will not decay because it will be escaping and it will propagate according to D'Alembert. I tell you, well, you will not escape too long, right? Why? You could be this wave that is traveling to the right, but eventually when getting to the boundary, this wave will bounce back. And after some time, the wave will penetrate into the damping region. Or you say, well, I could not succeed with this one. Of course, if you take such a wave, you don't escape either because this wave goes immediately into the damping region. But you could also think on, oh, I will escape moving to the left. So I do this, but unfortunately, when I get to the wall, right, there is a reflection and then eventually I will get into a small omega. So, the comment I'm making is that even if the damping region, a small omega that I can assume is just an interval AB, right, in 0L, is localized, all rays propagating left and right enter the damping region in a finite time. Okay? So what will be the time? So if we are in this example where, the string is of length 0L and the damping interval here is AB, right? So this means that the segment here to the left will be the segment 0A and the segment here to the right will be BL. Could you please tell me, right? The question is, how long do we need to wait until we can guarantee that all waves get into the damping region? What will be the time needed to guarantee this? Okay, so maybe it's a good time. I let you think on this. Maybe by the time we finish the break, you have the answer to this question, and then we move on, right? So that's a very interesting example to see that indeed in mechanical systems, in the context of mechanical systems, there is indeed some hope that localized damping will be able to be effective, right? So, but then please think on this question. So, okay, so what is then the time needed for waves to effectively get into the damping region? You see the time here on the left, the maximum time will be the time needed for waves to travel this direction and then go back. And the time needed in this case will be this and then bounce back. So the time will be simply twice the max of A and L minus B. So you see that indeed, even though this is a mechanical system in which it's a continuum mechanical system in which the damping is only effective in this small patch, there is some hope to achieve the exponential decay, even if it needs some time to be effective. So let me give you an example that illustrates very nicely what's going on, which is also relevant to other purposes, is that of the transparent boundary conditions, right? So how do we express this? So let me get back to the drawing, right? So this is t, this is x, this is the length L, right? So waves are propagating inside this domain, right? And then we have waves that are, traveling to the right. These waves fulfill the equation dt minus dx is equal to 0, right? So when we get here, I would like to impose a dissipate boundary condition of the form dt plus dx of y is equal to 0. So my claim is that when I consider the system, which is the free D'Alembert equation on the interval 0L, and I impose the boundary condition x equals 0 without any damping at x equals 0, and yx plus yt equal to 0 at x equal L, so for t positive and for t positive, this produces the vanishing of waves in finite time, right? Why is that true? Well, the reason is the following, we have this boundary condition yt plus yx equal to 0 on the right? And then, right, the fact that, here inside, the equation can be written as dt minus dx of dt, maybe I should, yeah, I think that is correct, dt plus dx is equal to 0. What does it mean? It means that this condition here, right? This condition here, right? Let me see. This is this front. This is this front. So I should maybe rather take the opposite sign, right? So maybe I should take here, sorry. I should take here maybe plus, right? And then maybe minus, right? Okay. So then I take here maybe minus. Okay, so it's one or the other. So the idea is that if I impose this condition here, right? If I impose this condition here, because the wave equation can be decomposed in this manner, the fact that this condition vanishes on x equal L, and that this condition, according to this writing of the equation, is transported along this characteristic field, when I get here, right? When the wave gets here, I will have the condition yt minus yx equal to 0, right? But if yt minus yx is equal to 0, then this means that because I also have y0t is equal to 0, this means that yt0t is equal to 0, right? I will also have above this point, so after t equal to 2L, I will have both the Dirichlet and the Neumann condition equal to 0. So then we will be in a situation where, right, if I draw the system again, x, t, and L, right, after time 2L, I will be in a situation where over here, y is equal to 0 and yx is equal to 0. But then there is some magic on the wave equation, right? Because the wave equation, you see, this happens only 1D. The wave equation can be written in this form, but you can also reverse the sense of the variables and write it in that manner. What does it mean? It means that now, right, you could reverse the sense of time, and then using the classical formula for the D'Alembert solution, right? Because, both the Cauchy data in the space-like direction, y and yx are equal to 0, the solution will be here 0 inside. So after again some time which is equal to L, you will have that the solution is 0, right, over there everywhere. So what we are simply doing is we call transparent boundary conditions. Why? Why do we call them transparent boundary conditions? Because these are the boundary conditions that simply guarantee that waves, right, that are propagating to the right, thanks to the boundary condition here, they go away. Right? So every initial perturbation that travels to the right, when getting to this boundary condition, it goes away. And this is why we call transparent boundary condition, right? And on the other hand, of course, right, if there is some signal traveling to the left, there is some signal traveling to the left, this signal will bounce. There is no damping effective on x equals 0. It will bounce, but then it will travel to the right again. And when getting here, it will be, you know, again, vanishing of the boundary. And this means that all the initial perturbation, after some time, that is actually 2L, will simply escape the domain and will reach the equilibrium, right? So in this particular case, what we see is that because waves bounce back at x equals 0 due to the Dirichlet boundary condition, but escape the domain zero L when getting to x equal L due to the transparent boundary condition, right? After a finite time, t equal capital T, the solution reaches the equilibrium, which is y x t equal to 0 for all x and for all t greater than 2L, right? So you see here the reason why the boundary condition is called to be transparent. Some people call it also perfect boundary conditions, right? So this is the transparent boundary condition or perfect boundary condition. Okay, so this is a one-dimensional example. Now, what is the link? What is the link with the problem in which, as we were considering before, right, the damping effective here will be sufficient to guarantee the exponential decay of the solutions? Well, because basically the damping we are realizing here will have a similar effect to, you know, boundary conditions which are transparent here and there, right? So the damping here in the yellow segment, what produces is that, you know, waves that are coming from the left to the right, when getting to, you know, the set small omega where the damping is effective, will nearly die, right? They don't completely die. You will not get something as nice as y equal to 0, but you will get an effective exponential decay. And for the same reason, waves that are coming from the right to the left, when getting to this damping region, they will decay, right? So this explains, right, this effect explains the effectiveness of a localized damping on the exponential decay of solutions. Good. So why these boundary conditions are called transparent or perfect? I mean, I mentioned that in some sense it's simply because waves, when getting to the boundary, they go away, right? So it's called transparent boundary condition because the boundary condition is acting as if there was no really, boundary condition over there, right? So it simply behaves like a transparent wall that lets, waves go away, right? So this has an interesting use, right? On numerical approximations. What is the application? The application is the following. So assume you are computing waves, you are looking to some wave propagation phenomena, right? So waves are propagating here in a domain L that is very large, right? So you are looking to, for instance, the propagation of acoustic waves on a very large auditorium, right? Or you are looking to waves on the ocean, right? So the domain is very large. It's nearly infinity, right? Corresponding, if you compare it to the wavelength, it's very, very large, right? It can be infinity or can be very large, right? So if you will do numerical schemes for doing this, then you will need to introduce a grid, right? A grid that will be necessarily of a small size to capture high frequency waves, but on the other hand, needs to occupy a very large region in space, right? So this will lead, right, to a very high dimensional right? Numerical discretization, right? And because the system we achieve by numerical discretization will be very huge, right? The computing time will be extremely large. To the point that eventually, you might simply not be able to compute, right? The propagation of waves on a very large domain for a large time window. Will be simply computationally too expensive, right? Somehow the problem is related, maybe more graphically, we will say, well, listen, this is like, I'm working in my computer, so, I'm doing numerical simulations, I'm doing the visualizations on my computer, and I want waves to fit on the screen of the computer. Yeah, but the domain is huge, right? So I will never be able to see on the screen of my computer, regardless of whether I have a 12-inch or 25 inches. This doesn't really solve the problem when the domain is huge, it's very large, right? Then people thought, okay, so, then maybe what I should try to do, right, is that even though the domain in which waves are propagating, if my computational domain is much smaller, right? So this is what I really see. Right? It would be great if I could simply reduce the PDE to that domain, right? But then people said, well, listen, but this is never possible, right? So even for the Laplace equation that we were considering yesterday that motivated the domain decomposition method, right? If you give me, right, even the Laplace problem, minus yxx equal to 1, y0 equal yl equals 0, the response of the system is global, right? I cannot claim that the solution of this system will be the same as solving the same problem with an artificial boundary condition here. right? Because then this will produce this, a small deformation that is very far from the actual behavior of the solution. So as soon as you, out of a very large domain, you reduce the PDE to a smaller computational domain, you have to pay very much attention to the boundary condition you have imposed, right? So this will be a wrong boundary condition that will be artificial, right? Artificial because it's not really related to the actual behavior of the solutions. The solutions globally, they don't obey at all to the condition that y at L is, sorry, this will be L prime, right? So some L prime, small, right? So this is the L prime. They will not obey to these artificially imposed boundary conditions. Why? Because the solution of the PDE is a global problem, right? This is something that it takes some time to understand, right? Because we see the PDE as being a local operator. It's true, it's a local operator. I'm just taking two space derivatives, and in order to compute two space derivatives of a function, I can do it in an interval that is as small as I wish near the x. But when I am solving the problems in mechanics that also involve boundary conditions, the problem is not local anymore. You see how the response depends on the amplitude of the domain in which, in this case, the Dirichlet-Laplace problem is formulated. So, this very natural idea that, even if the phenomenon under consideration is global, I want to compute it locally is very natural, right? You see that you cannot do it so easily, because if you will impose, the artificial boundary condition just by mimicking the Dirichlet boundary condition on the global domain, you will catastrophically fail, right? Then, if you go to wave context, right? If you go to the wave context and you formulate the same problem, you will have the same concern. I'm trying to solve a wave propagation problem here in the large domain, but actually I can only access, what fits in the screen of my computer, or what I simply can compute, right, with the computational resources I have, which allow me to solve very large systems, but with a given threshold. I will not be able to solve system given, beyond this threshold during the time window I am given, right? The computational time will be much higher than the time, right? The real time. This is actually the challenge in, in computational sciences, right? It's not simply about claiming theoretically by numerical analysis that I have a numerical method that is able to compute the solution of a given process during the time interval 0, 1. If you really want this to be, usable, you really need also to be able to compute the solutions on a computing time which is small with respect to the actual evolution time. Otherwise, for instance, if you were doing computations in order to apply a feedback mechanism, you see that this will never work, right? Because, waves are evolving in time 0 to 1, right? And then you have to compute the feedback mechanism, and you say, oh, but wait a second, because, in order to apply the feedback mechanism, right, I need a time, computing time of the order of 100. Yeah, but then it's too late, because waves are not traveling within the space interval 0, 1 anymore, but they are at the distance 100. So the fact that, the computational algorithms need to be efficient, so to be able to capture solutions nearly in real time is a must, right? In particular, when you are doing feedback control, right? So then people said, is there any chance that when I am solving, right, the wave equation over here, right? Is there any chance when I am solving the wave equation over here, right, that if right? I, you know, try to confine myself to this domain. The fact that I impose a boundary condition here doesn't produce an artificial bouncing. You see, generically, if you take any hard boundary condition like, Dirichlet or Neumann, these boundary conditions will produce that wherever you take a signal that is propagating to the right, when getting to this boundary, it will produce a bounce. And you will say, fine, I mean, computationally, I can see this phenomena. Yes, but people telling you, considering the global problem, they will tell you this is a numerical artifact, right? So then this will become a numerical artifact. This is an spurious solution, simply meaning that this is a purely numerical but not true solution. Why? Because when waves are traveling on the full domain, they cross this point where there is no real boundary. The boundary you impose it because you really wanted to make your computational domain fit the screen of your computer. Waves propagating in the large domain don't see this wall, they just go through, right? And you willing to confine your computation to this left subdomain in order to get a numerical scheme that is able to give you an approximation of the solution, you decided to take, for instance, either Dirichlet or either Neumann boundary conditions. But this produces this effect that waves bounce. So if you were doing this, then this is what you will see, right? And you will claim, oh, you see, I have computed the solutions of the wave equation in this large domain, and I have observed that there is a kind of phantom point here. There is a phantom wall that produces the bouncing of your solutions. I mean, people knowing the physics of the problem, they will tell you, no, this is not true. Waves propagating freely in this domain, they will go through all the domain and they will never bounce in an interface that doesn't exist. So the solution you computed here is wrong. It will never reflect the true physics of the problem. This is why, even though we might indeed need to confine ourselves to a finite domain, right? On this interface, we need to be careful about the boundary conditions we impose. And then the boundary conditions that we take will be the transparent boundary conditions, right? So one of the motivations of the transparent boundary conditions is not simply as damping mechanisms for the mechanical system, so to guarantee that the energy is dissipated, is something of great use also for developing effective computational methods for wave propagation, right? Because these are the boundary conditions that allow you to confine computations to a given domain, right? Without generating numerical artifacts, right? So, the conclusion is that transparent boundary conditions allow to confine wave computations into subdomains without introducing spurious numerical components generated by the interaction with the artificial computational boundary. Okay. This theory has been very much extended in order to, for instance, develop the theory of perfectly matching layers, which also works in multi-D. Okay, so let us precisely discuss multi-D waves. Let me discuss multi-D waves. So what is the difference between 1D waves and multi-D waves? So in 1D, everything is very simple. Solutions are given by the D'Alembert equation. And all this is very much related to this very, simplistic, but on the other hand, useful decomposition of the D'Alembert operator into two propagating first-order transport equations, one to the left and the other one to the right. Okay, good. So from a mechanical point of view, there is not, from the modeling perspective, there is not a big difference, right? So in 1D, if you are considering, the elastic string, you take the one-dimensional wave equation, and if you move to, for instance, 2D, like the elastic membrane, you consider the same model, except for the fact that, of course, now the second order space derivative becomes the Laplacian, right? So from a PDE perspective, things don't change very much. Of course, the geometry changes, right? You go from a trivial one-dimensional geometry where, you can just consider strings, right, into the wall of shapes, where now the PDE evolves inside, this cavity, and the geometry of this cavity can, be relevant, for the evolution of solutions, right? Then what do you expect when we are considering, waves in a two-dimensional domain? The same could be said in multiple dimensions, right? So the best we can do in order to understand, at least a priori, right, the behavior of waves is to consider the so-called Gaussian beams, right? So these are high-frequency waves that one can compute by computed or defined, because this is analysis, there is no numerics on this. This is defined through geometric optics, high-frequency expansions. Okay, if we have time, we will come back to this. But let me give you first the idea. What do these waves do? Well, these Gaussian beams are like laser beams. They are solutions that will be very much localized along a given direction, right? So this is, you take your lamp or you take your laser, right? And then you will enlight, the laser in the direction, in a given direction. So given any point in a space, right, you could start the process, of course, in any other point as well. But I have chosen, the starting point to be this, right? I, send a ray of light in this direction. What happens to this ray when getting to this boundary? Well, this ray, when getting to this boundary, right? Let me erase these 2 points. When getting to this boundary, this ray will bounce back according to the Descartes law, so that, of course, the angle, the incident way will generate an outgoing wave so that these two angles are the same, right? And then when getting here, right? So then maybe you will generate another one that is going in this direction, right? And then, you know, you will have here again the same, you know, principle. And then you get here and you will have the same principle, right? And so on. This is one ray, right? And this ray will evolve forever, right? There is no damping in my model. If you don't put any damping, it means that the energy one you have put along this ray will travel, right, endless in your domain following the trajectory, right, of a Hamiltonian system with some bouncing laws on the boundary given by the Descartes law, right? And this is a mathematical billiard, right? So this is a mathematical billiard. So this is like when you play billiard, right, on a table with 3 or say 18 balls or wherever, right? You kick, you know, the billiard ball with the stick, then it propagates along the domain. When getting to the wall, it is reflected. I mean, on the true billiard, things are more complicated because the walls are elastic, right? And because the walls are elastic, there can be added effects that can modify the bouncing, you know, law of the sphere, right? In this mathematical billiard, things are much more simple because this is a rigid wall, right? So this is a mathematical billiard with a rigid wall, right? And therefore, you know, the spheres bounce like particles according to the Descartes law, okay? So this was one of the trajectories of the billiard, right? So this was the trajectory starting from here. Let me now take another trajectory, right? In here, right? Then this trajectory will come here, and then it will get there, and then it will come here, and then it will go there, right? And then here, 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 and so on, right? And then you can take another trajectory, maybe departing from here, right? And you will do the same, right? You will do something like this, and then something like this, and then something like this, and that, and that, and that, right? Okay. So you see that you generate then a dynamical system with a very complex dynamics that depends on the geometry of omega. Okay, in 1D it was very simple, right? Because you have just one segment. The only thing you can do is travel to the left or travel to the right, right? And then bounce back on and forth on the boundary, and this generated a periodic, time periodic motion of period 2 times the length of the space interval, right? Here you see that the motion looks much more complicated because the dynamics of the ray will very much depend, right, on where the initial signal was localized and in which direction you started, because you could start, of course, also at the same point, you know, you could also start on this initial point, but move in this direction, and then this will generate a different trajectory, right? So the trajectories depend on, say, 3 parameters in this case, right? The initial position of the ray, and then the angle of exit of the ray, right? So 3 parameters. So you will have a dynamical system, right, that will evolve not in R2, but in R3, right? Because whenever you try to determine where the trajectory is, you will need to show, to tell where is it located in space, x1, x2, right? But also in which direction it's oriented, because it's not the same being here oriented in that direction or oriented in a completely different direction. This is a very complicated dynamical system. Do you think this dynamical system will be periodic? What do you think? Will this dynamical system be periodic? In 1D it was. And then, of course, in analysis of partial differential equations, in analysis of models in mechanics, right, the same will happen with machine learning problems where you are considering these neural networks. You see, you could think on this as being, you know, also the output of a neural network layer by layer, right? So this clearly illustrates why the analysis also of neural networks is so difficult, right? Why? Because yes, I mean, you guess you have an idea of how the dynamics is evolving, but then you realize out of this example that depending, right, the behavior of solutions not only depends on what is the system you are considering, but actually also where you are putting the initial energy. What is the, for instance, the image you are classifying, you are making evolve along this neural network. Because you see, if you think on this as being a classification mechanism, you will say, well, I mean, this classification mechanism is very complicated. Because if I start at this point in a direction, I go, you know, along one ray, and as soon as I change the direction a little bit, you know, I completely modify the trajectory. I don't see it for a short time, right? Because in the beginning, the gap in the angle is very little, so there will be a divergence that, you know, in short time intervals will be negligible. But after the first bouncing, you see how these two trajectories, they have nothing to do with each other anymore, right? So this is why, you know, we talk also about the generalization property of neural networks, right? Is very much related to the stability of the dynamical system, time discrete or continuous, generated by the neural network, right? Because if a neural network will behave that way, that will be quite catastrophic, right? Because it will mean that you take a picture of a dog, then, you know, it goes to the set of dogs, but as soon as you change a very small feature, right, the picture goes in a completely different direction, and you say, well, it's not a dog, it's a crocodile. This will not be good, right? But this is how things behave. And this is why when you are designing an acoustic, opera hall, right, you have to make a lot of attention, you have to pay a lot of attention to the geometry of the hall and also to the materials you are using on the walls, right? Because the geometry matters, right? But the materials are also important because they can, for instance, help on making some of these bouncings to be milder, right? And this is what happens actually, as we said, in the true billiard, where you can play with the, rotational effects on the ball you are kicking, because then enjoying of the elastic properties of the ball, you can, make that the bouncing doesn't occur according to the Carr law, but for, along much more subtle, right, collision and interaction effects. So do you think that these dynamics will be periodic? Well, obviously not. Obviously not. I can give you another example where you can see the lack of periodicity, right? And these dynamics will not be periodic except in dimension d equal 1, right? So this is a very prototypical example, right, in which you see that the understanding of the evolution system in one space dimension, of course, tells you some important features. For instance, we learn from the D'Alembert formula that the propagation with finite velocity of rays is a nice way of describing the actual motion of the solutions. But our extrapolation, if we will extrapolate that because in 1D solutions are time periodic, they will be also time periodic in the multidimensional case, this is totally wrong, right? So I give you another example. For instance, when you take the domain omega to be a rectangle, right? Right. So this is 0, L1, and this is 0, L2. Could you please tell me what will be, so this is omega is a rectangle membrane, which is actually the shape of the billiard table, right, in which we normally play, right? Or a soccer field or a tennis field. So could you please tell me what will be at least two very distinguished dynamics I could encounter in here? Could you give me two of them? So there are two of them that are very special, right? So one will be this horizontal ray, right? So you start anywhere, you go perpendicularly to the boundary, then it bounces back, and then, you know, the wave will propagate back and forth, and back and forth forever in this horizontal segment, right? Good. Is this ray periodic? Yes, it is periodic. It's like in one space dimension, right? So this will be periodic with period 2L1, right? Very good. Now, for the same reason, I should also consider the vertical rays, right? So then this will generate, right? If I start here, I go up and then down and then up and then down. Oh, this is periodic as well. What is the periodicity of this ray? Well, if this length is L2, then this will be periodic of period 2L2. Oh, and then you say, well, listen, you know, if all rays are periodic, then maybe there is a common period for all of them. And then my question is, can you say that if you have an horizontal motion that is periodic with period 2L1 and a vertical motion that is periodic with period 2L2, can we claim that there is a common period for both of them? So if I give you a function with a given period and then another function with another period, tau1 and tau2, can you say that there is a common period for the two functions? Will the sum or the maximum of the two periods be a period for the both functions simultaneously? So what do you need? I give you a function. So maybe written more simply. So I give you a function ft. So tau1 periodic, right? F1. And then I give you another function f2, tau2 periodic. The question is there a tau such that F1 and F2 are tau periodic? This is the question. What do you think? Do you hear me?
Okay, sorry, I don't know whether the signal is going through well. Can you hear me? Oh, yeah, okay, thank you. Well, so in general, not, right? So the existence of such a tau depends on the fact that tau1 over tau2 are rational or not, right? So if tau1 and tau2 are mutually rational in the sense that the ratio is rational, then there is a common period, right? But, you know, if tau1 divided by tau2 is irrational, then there is no common period. So you see already by this example that if you give me the simplest rectangular membrane with lengths L1 and L2 that are mutually irrational, right? Already in this example, you see that, you know, the billiard is not periodic anymore. And this will show you that the solutions of the wave equation in the multidimensional domain are not periodic anymore, right? And of course, other than this, you could consider many other rays that behave differently, like for instance, this one, right, that does this, and then 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 this, and so on. Or I don't know, you could also take a wave doing this, right, and then this, and then this, and then this, right? So there are many different patterns you could generate. So this is not a periodic motion, right? So this is the first thing to keep in mind. When you move from one-dimensional mechanics, one-dimensional waves to multidimensional waves, you can keep some of the ideas in the sense that, you know, propagation along characteristics, in this case, we call them bicharacteristics. Propagation along characteristics is fine, but other issues like, you know, periodicity, I mean, they are a dream, right? This happens only in 1D because of these very trivial, right, dynamics. Okay, so what is the perfectly matching layer? The perfectly matching layer idea is the following. So you recall I said the problem is that we are computing waves on a very large dimensional, I mean, a very large size domain, maybe the whole ocean, or I'm propagating acoustic waves in the whole country. Of course, I cannot make this computation to be viable, to be doable on the computer, right? So I need to confine, right, into a given computational domain. And then this requires something like transparent boundary conditions, right? Because I need to impose here on the boundary, for instance here, I will need to impose a transparent boundary condition, right? So that whenever the ray comes in, right, there will not be bouncing and the ray will go out. This is the idea of the transparent boundary condition. Good. But can I realize that? I say, well, in here, because you give me a very clear, say, transport line, I can probably do this for the green ray. But then I realize that actually, whenever I am sitting on the same point, there can be many other rays incoming, right? There could be, you know, the purple one coming from this side. There could be the blue one coming from the right with a different angle. There could be, you know, the orange one coming here, almost tangent from the left. There are so many rays that I will never be able to find one single boundary condition which is transparent for all the incoming rays.
Of course, in 1D, the problem is simple because when you are sitting on the left, the only thing you see is one single ray coming. So you can adjust the boundary condition. Is dx plus minus dy dt equals 0. And when you are on the right, the same. You know, when you are on the right in 1D, only waves can be coming from the left, always, you know, along the domain, right? And therefore, you can impose the boundary condition at x equal L to be dx plus minus dt equals 0 with the corresponding signs, left and right. So in 1D, this is possible, but in multi-D, no, because even if you are sitting on a point of the boundary and you try to determine what is your transparent boundary condition on that point, right? What you see is that waves are coming in all directions, and there is no possibility of building one single boundary condition that is good for all of them. Then what people did, I mean, and this was an idea by the French mathematician Van Berger, what people did was the following. They said, so maybe before, rather than trying this, I mean, you see, even the computer or even the iPhone or the iPad, they have a frame, right? Right? There is a frame in which your screen is fitting, right? To make it more, say, robust, right? So let us put a frame. So this is perfectly possible. Even if you tell me that my computational domain is this, say, orange rectangle here, right? That I can, right, fill with this now green color, right? This is my computational domain, right? Around this computational domain, I can put also, you know, a thin layer the frame, right? And then what I do is, you know, I write down a wave equation that is going to be precisely something like this, where omega is precisely this neighborhood, this frame all around the boundary. So what is the phenomena then I expect? Recall that 1 over omega is 1 in omega and 0 outside omega. So what is this wave equation doing when evolving according to this dissipative wave equation? What the wave equation is doing now is, while we are here inside, waves are propagating freely without any dissipation, because here inside, this is omega minus small omega. Here inside, this damping term vanishes. So waves propagate completely freely without any damping, without any dissipation. And when they get here to this frame, which is a neighborhood of the boundary, they penetrate into the set where small omega, right, is damping. So what waves do is they travel, right, freely over here. They get into the damping region, right? And if the damping region is effective enough, then basically, even if they want to bounce, right? Even if they want to bounce and they bounce, the energy of the bouncing is nearly negligible. It has to go through again all this dissipative region, and when it gets there, nearly there is no energy left, so that, you know, very little comes. So in this way, eventually by regulating the damping with a constant, right, we can generate dissipative effects on this, you know, neighborhood of the boundary, which will make, you know, this perfectly matching layer. Why is it called perfectly matching layer? Because now we are not trying to achieve the dream that we got in 1D. In 1D, we were able to write the transparent boundary condition just on the boundary, on the interface, but this was a miracle. Only happens in 1D because there is only one incidence angle for waves, because the domain is 1D. In multi-D, that is impossible. So what we do is we add an extra layer, right? So this is like a damping layer, right? Which will have, you know, the effect of an absorber of energy, right? And this is what you see very often, right? When you are designing rooms with very good acoustic properties, right? If you want to avoid, you know, resonance effects, very often you use soft materials on the walls, right? And this is what produces the fact that, you know, the energy, right, doesn't come back after an artificial bouncing, right? The same also when you are isolating houses in order to preserve temperature inside, you know, and avoid a too high expense on the energy to keep the home warm. Oftentimes, the homes, you know, the traditional homes are now covered with soft materials, right? These materials, in that case, are made just in the opposite direction, so that, you know, the whole signal propagates, in the sense that the heat, you know, propagating inside will not go away, but will come back, you know, on this interface to the inside, right? So we are here considering situations where we have one layer. One layer is the inner layer where we live, where we are considering the acoustic waves or the, you know, the heat waves, right? And then there is an external layer that is built simply as a gadget, as an instrument, right? In order to realize what we want. And what we want can be different, can be complete transparency, for instance, for waves, or it could be complete isolation for, say, heat waves, okay? So this is the idea of perfectly matching layers. And with this idea, you can get very, very, very far, right? Because you can eventually, right, also in this direction, build, say, composite materials, right, are based on this idea of layering, right? But rather than doing it at a macroscopic level, as we do here for the transparent boundary condition, because after all, it was just to, you know, try to compute within the screen of my computer and then use the frame in order to avoid artificial numerical artifacts, right? When you are really building new materials, you can combine, you can layer in a macroscopic manner, right, different materials, so to guarantee new effects, right? And this is, for instance, what you see in the theory of homogenization, right? So the theory of homogenization, right? Yeah. It talks about, you know, how, you know, the mixing of two media can lead to new phenomena. Okay, this is something also very important in control engineering, because as you know, right, so when you look to the modern cars or modern airplanes, I mean, they are basically done out of plastic, right? So these are new materials that behave extremely well, right? In the sense that you will avoid oxidation. The aircraft is lighter, therefore, you know, it will consume less energy, is more elastic in case there is any collision with any bird or any other, say, artifact. And it has, you know, optimal properties for, you know, the goal, right, which is the transportation, aerial transportation. Okay, so these are normally new materials. This is not wood, it's not metal, right, it's not stone, it's not water. This is a material that is a mixture, that you can generate in order to enhance properties, right? So why these things are tricky from a mathematical perspective? There is a huge theory of homogenization, right? Which is also very interesting in the machine learning perspective, right? It's like Floquet theory for dynamical systems, for periodic dynamical systems, right? It says, be careful, right? Because when you are simply dealing with, constant coefficients, everything is much easier to understand. As soon as the coefficients of your differential equation, your partial differential equation, or your machine learning algorithm depends on time, if you want to, depends on from one layer to another, then there can be effects that are not easy to have an intuition about, right? They could be unexpected. And when they are unexpected, they can be unexpected for good, but also for bad, right? Let me give you an example, which is at the basis of what is called the theory of homogenization, right? So the example is very simple. I mean, you are a mathematician, you have been hired in a laboratory of new composite materials. And, because you are the mathematician in this experimental laboratory, you are asked, okay, can you please tell us what is the behavior of a material that is mixed? I mean, is built out of a mixture of two materials, right? The yellow and the green. You say, well, this doesn't look to be so difficult, right? So how can I formulate this mathematically? It's very simple. I say, well, the mathematical problem should be, let me solve this equation, right? Right? So if this is a beam, an elastic string, then I say, okay, let me test how this is working. I apply force 1, and I try to see how, the deformation is ongoing. Now I expect something more complicated than the previous parabola, because of course, the fact that the elasticity coefficient varies from the, from the orange to the green regions, it means that the response of the elastic material will also be different in each sub piece, and therefore I will not get such a simple parabola. I will get some more oscillations and microstructure also on the response of this elastic material, right? Okay, but do you say, well, what is the epsilon? What is the link of this PDE with the problem before? I say, well, very simple. So I take sigma, right? I take sigma x, right, to be, 1 for x from, right, and to be 2 for, x from y to 2. And then I take epsilon, right, to be very small. So what I'm doing then? Well, what I'm doing is, on the space interval 0L, right, I am writing an oscillatory pattern with, a microstructure with characteristic size epsilon, right, and the material, is jumping, right, from one material actually to another, right, so that equally frequently is green or orange. And you see what happens with colors, right? So if I, if I mix two colors, right, like, right, I take purple, right, and then I take green, right? Well, I see a different color, right? Well, in the beginning, of course, you say, well, but this is not what you are doing. You are taking purple here, right? And you are taking green here. Yes, but then the pattern of repetition is so frequent that eventually, all the colors are getting mixed, right? And this is leading to a new color, which is kind of an hybrid between, green, right, and purple. And this is how composing basic colors, you can get many different patterns of colors, right? Okay, very good. So what does it mean mathematically? Well, it means this is the role of epsilon, is to make this pattern of, mixing more and more frequent. And then the question is, if I mix, purple or, orange and green more and more frequently, what are you going to see from a macroscopic perspective? What is the global effect you will see? Well, what you see is the following. You see that, you were trying to solve the equation minus sigma x over epsilon uxx equal to 1, right? I ignore boundary conditions. You can fix them adding some additive constants. This is not a problem. So I integrate this equation once, and then basically what I see is this, right? Because, I integrate once, the integral on x, goes away. I mean, the derivative in x goes away. Sorry, I get a minus sign. The minus sign here, I put it on the other hand. I, integrate 1 and I get x. So then I get that u, which of course depends on epsilon, is so that u epsilon x is minus x divided by sigma x over epsilon. Right? And then you say, oh, now I have to pass to the limit here. I have to pass to the limit here. And what I'm doing, basically 1 over sigma x over epsilon, right, is a periodic function, right? So, but this function, the periodic function, now is not anymore sigma, right? Is rho, which is 1 over rho x, over sigma x. And rho, now, if I look to the definition of what sigma was, if sigma was 1 in the interval 0, 1, and 2 in the interval 1, 2, right? When I go to rho, what I see is rho is equal to 1 in the interval 0, 1, but is how much in the interval 1, 2? Now is 1 over sigma, sigma being 2, this is 1/2, right? So, and what does the theory say? The theory says that if I take a periodic function, right, rho periodic, out of it, I build a sequence where I increase the period of oscillation and I let epsilon go to 0, in the limit, this weakly converges. I mean, you can write weak convergence in L2, or if you want, in the weak star topology of L infinity, this is not so relevant here. You converge to the average value, where the average value is, because the period is 2, is 1 over 2 times the integral from 0 to 2 of rho x dx. And now, because rho is given piecewise, is 1 in the first interval and 1 over 2 in the second interval, this is 1 over 2, then 1 plus 1 over 2, right? And this is what? This is 3 over 4, right? And then you see, oh, miracle. So it turns out that out of this problem, minus u epsilon x equal, or sorry, u epsilon x equal to minus this, which is minus x rho x over epsilon. This converges to minus x times 3 over 4, right? And then if I write the limit equation in a PDE manner again, right, I put the 3 over 4 on the other side, then the limit will be, right, something like this, or if you want, minus 4 over 3 Vxx equal to 1. So what did I show? I mean, what I have shown is that through homogenization theory, right, combining two materials with, properties 1 and 2 in an equal manner on a periodic, rapidly oscillating pattern, combining materials 1 and 2, what I get is a new material which is with coefficient 4/3. What is interesting here, I mean, first, I mean, this computation is, of course, very interesting analytically, and you can solve this. I mean, you can prove that. You can prove that if you solve the, you know, this Dirichlet problem, the solutions are bounded in H10, and that the weak limit of the solutions is the solution of the corresponding Dirichlet problem with, you know, the new diffusivity or elasticity coefficient 4/3. What is even more interesting here is that the way of averaging sigma is nonlinear. So the warning is the averaging process is nonlinear. It is not done at the level of sigma, but rather on, you know, the inverses, right? So this is why homogenization theory not only allows you to build new materials out of, you know, composite materials out of two basic materials, 1 and 2, but also is not so easy to understand, because our intuition will be that what? That if I mix 1 and 2 equally, then I should get the average, right? Which is 3/2. Well, I don't get 3/2, I get 4/3. Why? Because the behavior of the mechanical system, again, is not seen at the level of the PDE, but rather at the level of the, you know, resolvent operator on the green function that is giving me the solution of the PDE out of the PDE, okay? And this is something also very important in control theory, because oftentimes we are not simply considering control problems A and B, or control problems for a constant coefficient wave equation. We are dealing with these complicated scenarios, and we need to understand, right, what is the actual behavior of these complicated solutions to design proper control mechanisms. The same will be, you know, in the context of machine learning. Be careful, right? Because in all these complex processes, when we are dealing with, you know, deep neural networks, you know, composing layer by layer, layers that are, you know, switching, that are changing, be careful. The overall behavior of the system is not necessarily our very, you know, simplistic average we do in an intuitive manner. Keep in mind that in this context of complex dynamics, the intuition probably is too simplistic, is often too simplistic, and doesn't lead to correct answer.